David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. Subject we're talking about today is moments by cross product. We've just discussed how a moment is a force times a distance, or force at a distance, and we used a scalar method to figure out moments. We're given this basic setup here of on an XY coordinate system. Start off kind of simple. We have a force F and a vector R with an angle theta between those two vectors, and we say that the moment, which really is about the z-axis coming out of the board at me, is the moment, and it's expressed as a vector. It's like that, and I'll show it kind of as an arrow. Should be coming out of the board. I can't draw that, of course. By the right hand rule, it's coming out of the board at me, so its direction of rotation is counterclockwise about that axis. And I can also express it as the scalar magnitude of the moment times the k unit vector. Another way of expressing it is, so it's this MO in the vector formula is R cross F. The scalar numbers of those are the magnitude of the moment is equal to the scalar value of R, the position vector, times the scalar value of the force vector F, times the sine of theta, where theta is this angle between their lines of action. Okay, we have to go back and talk about a few of the properties of cross products. First, it is not commutative. R cross F is not equal to F cross R. It is equal to negative F, the vector, cross with R. And I've shown that over here in this drawing where I take my vector F. I'm also, you got to remember that I'm using the first vector in this cross product is the position vector. It starts at the point where I'm taking moments about, so I have to move F and reverse its direction to make it negative F and put it here originating at O and going off still in its same line of action but in the opposite direction since. And then at its tip I move the vector R, because it's the second one in this equation right here, negative F cross R, so its tail is at the tip of F and it goes off in its direction that it was over here. So that produces the same moment about point O, negative F cross R. We'll look at that here and again in a second. Well, let's look at it right now. In 2 dimensions, I have unit vector. The unit vector I is a unit vector length 1 in the x direction. If I cross it with a unit vector j in the y direction, I get what I've been getting here, a k unit vector. But if I cross j with I, j cross I get negative k. So it points into the k vector, negative k vector points, unit vector points into the board. We'll see more about that in a second here. Other properties are of scalar multiplication. If I have the scalar number S times R cross F, that's equal to, I can put the scalar, multiply it by vector R and then cross it with F, or I can multiply the vector R crossed with the scalar times the vector F. There's also the distributive property. R cross F1 plus F2 vectors is equal to R cross F1 plus R cross F2. Of course, F1 plus F2 gives us a resultant, so this is not earth-shattering. Now I've talked about it in 2 dimensions. I want to extend it out in 3 dimensions. I want to add In addition to these properties of two dimension, where I cross j is k, j cross I is negative k, I want to extend it out and talk about how j cross k is positive I, but k cross j is negative I. So I reverse that direction when I reverse the order that I'm doing the cross product in. It's kind of like this sort of proof over here with the different axes. Similarly, k cross I is equal to j, but I cross k is equal to negative j. And then we see that I cross I is equal to 0, j cross j is equal to 0, and k cross k. I can kind of see that if I just put an I vector. I can't cross it with itself if it's the same direction, because there's no angle between it. So any vector crossed with itself is equal to 0. So I want to continue this logic, and I'm still looking at what r cross f is, which is a moment. If I express r as Cartesian form, rx, ry, and rz, and I express f as fx, fy, and fz times their ij and k components, then if I cross r with f, r cross f, I'm going to multiply all the terms together. I have to multiply the rx times fx, rx times fy, and I've also got, from the scalar and distributive properties, I keep my i's and j's, I cross those with them, and these are scalar numbers that I'm just multiplying together. So I have to do it 9 times. I have a 3 by 3 grid. Rx has to cross with all those f terms. Ry has to cross with all 3 f terms. Rz has to cross with all 3 f terms. And so I just write it all out like this. Rx fx, I cross I, that's equal to 0. Rx times fy, scalar numbers, times I cross j, which from over here is k, unit vector, plus Rx times fz, scalar numbers, times I cross k, which from up here is equal to negative j. And I extend that on out, keep doing that with all 9 of my terms, and I can eliminate the ones that are 0, these 3, I cross I, j cross j, k cross k, and I can combine my k terms, my j terms, and my I terms, and I can rewrite this whole thing as r cross f is equal to ry fz minus, because I get a minus sign up here, there's where my minus is getting in there, rz times fy, the whole thing times the I. So I can just do it, these are just numbers I'm multiplying together. Continue the same thing for the j terms, gather those up. Remember that these are just scalar numbers I'm multiplying together and then adding or subtracting. Same thing for the k. So I've then got a way to evaluate that is equal to the moment, m0, mo for the origin. In this example here, if it was 3 dimensions, which I haven't even tried to draw because it's impossible for me to draw it clearly. So we're just having to think about this conceptually. Anyway, this is a way to evaluate m cross m. The moment about any point is the position vector crossed with f. I just multiply those terms together, and I got a scalar. So this moment is also a vector in 3 dimensions too. So it's just this Cartesian components of the vector, MO.